Hi everyone, I would like to show you how to derive the second-kind Lagrangian equation from the Hamilton principle with non-holonomic constraint. So we have got the non-holonomic constraint equation and we will start the derivation from the Hamilton principle. So dt denotes the kinetic energy that depends on the qk, that qk and t. So take its variations. The variation of the time t will be 0 according to the virtual displacement theory. It's a partial t over partial t dt equals to 0. Now we substitute this formula into the Hamilton principle, so we can get this expression that equals to 0 again. dt equals to 0, yes. And now we have to apply a dirty trick through the time derivation rule. So we have to derivate with respect to time the partial t over partial qk dot dqk and dot. So according to chain rule we can get this formula. Anyway, it's a well-known formula, but I write this. So we can find this last term in this former expression. So we have to arrange the equation for this part. Partial t over partial qk dot with respect to time, yes, equals to partial t over partial qk dot dqk dot. And we have to substitute this expression into the Hamilton principle, so we can get this form. And rearranging the equation of the Hamilton principle and multiplying out with the dqk dt, we can get this better form of the Hamilton principle that equals to this integral, this portion of the integral. Yes, and we have to keep in our mind a rather important remark in connection with the term that I have denoted. So, namely, we can write this term into another form, and at the end we can calculate this assigned mathematical operation more easily. So the mathematical problem is reduced. So the question is, what will be the values of these terms at the limit? So at the t1, at the t0. So its value will be 0 because, as we recall our knowledge about the virtual displacement theory, so between the 2 points the virtual displacement has any values but non-zero, but at the boundaries, at the t0 and t1, it equals to 0. So as a reminder, I show you how could we get this 0. So I have written the true path and the wild path, qk prime, and qk prime minus qk is the dqk, and the qk0 is also 0, and the qk prime is also 0 from the qk prime t1 minus qk t1 equals to 0, and dqk at t1 and dqk at t0 equals to 0. So these two terms will be 0. It's proof. And now I just highlight the result. Right. And naturally we shouldn't forget the virtual quantity from the figure. So after that, writing at the first row the Hamilton principle, that equals to 0 because of the former causes. And in the second row I can write the constraint equation that contains the lambda as a Lagrangian multiplier because of the non-holonomic constraint. So we can realize that we can match these two equations and we can write one expression from these two ones. Naturally multiplying out with the dq key dt that equals to 0 again. And here we can find the virtual quantity that we have talked about before. So it is non-zero, arbitrary but non-zero because of the mentioned causes, you know. So we can get 0 if this part will be 0, so it must be 0. So the final equation is the qk plus lambda j for jk minus partial t over partial qk dot again minus partial t over partial qk yes, and the non-holonomic constraint equation plus beta j equals to 0. So this is the final result, but from the first equation a 0, so the equals to 0 is missing. And I would like to show you a special case when the system is conservative with non-holonomic constraints. So we can write that the qk will be partial t over partial qk dot minus partial t over partial qk, and the qk is minus partial v over partial qk, and v depends only at the qk and the t. And we can write that substituting the minus partial v over partial qk at the qk, and if I add this term to the right hand side also, I've got this t minus v at the numerator, and for the second term is also true. And the main question, why I have written there the t minus v as well. It is very easy to explain. As we could see, the v depends only on the qk and not on the qk dot. So I can write the partial L in the first, and I can write the partial L in the second term as well. It is very easy to see we will get the same result in this case.